So in the final section of this chapter, we're going to start talking about gases, kind of how they behave, different calculations you can do with them, so on and so forth. So gases will expand to fill their containers. So we talked about this in the first section of this chapter. Okay, whatever container they're put in, whether it's outside, whether it's in a room, whether it's in a vial, anything like that, they will expand out to fill their containers. Okay. They do have low densities because of this, because they can have massive volumes, and they are compressible. Okay. And they're compressible because they are mostly made up of empty space. You have these few atoms spread out everywhere. So going back to when we talked about density and how you can identify different substances based on their density, okay, it's actually difficult to do that with gases. You can, because gases will have a set density for whatever their compound is, but you have to have very specific conditions met in order to measure the density that way. So gases will also exert pressure on their containers. So they're constantly pushing out on their containers, okay, which exerts that pressure, okay? So we've got the volume, we've got the pressure, and then we're also going to add in temperature of the gas, okay? So there are three major gas laws that we're going to talk about, and then we're going to talk about the combined gas law, okay? So first up, we've got Boyle's law. So Boyle's law relates volume and pressure. And with Boyle's, I always remember that because I think about, like, if you get a boil on your skin, okay, there's a lot of liquid in there, so there's a volume, and then you can also push on it and there's a lot of pressure there. Okay, so that's how I remember that it's volume and pressure for Boyle's law. So for a constant amount of gas at a constant temperature, okay, so we're not changing the amount of gas and we're not changing the temperature here. Volume of a gas will increase as the pressure decreases. So you can kind of think about this as if you've got like a balloon in your hands. And if you're pushing on all sides of the balloon, you're actually going to start decreasing the volume that's in that balloon. Okay? And then as the volume of a gas decreases, the pressure increases. Okay, so that's the example with the pushing on the balloon thing. Okay? But then if you think about increasing the volume, okay, the pressure is going to decrease because you've got more room for that gas to move around, so it's not going to be hitting that spot on the container all the time or as frequently. Okay, so this leads to the first gas law. P1 V1 equals P2 V2, where P is for pressure and then V is for volume. Okay, so in this way, if you are given three of these variables, so if you're given the initial pressure, the final pressure, and one of the volumes, you can calculate the other volume. Okay, and then so that works for any three variables in this equation. If you're given three, you can calculate the fourth. Okay, so this is kind of an example of that. So you've got a decreased pressure in this first one because you've lifted the piston up. So the gas particles get to spread further and further apart, which increases the volume. Now in the second example, you increase the pressure by pushing down on the piston. Okay, so that compresses the gas particles. They're pushed closer together, so the volume decreases. Okay. All right, so now we get into Gay-Lussac's law. So this relates temperature and pressure. Okay, so for a constant amount of gas, so again, we're not changing the amount of the gas, and in this time, we're not changing the volume of the gas either. That's going to stay constant. So the pressure of the gas will increase as the temperature increases. So if you increase the temperature, you're causing those gas particles to bounce around more and more and more. Okay, so they're going crazier, right? So that's going to increase the pressure on the sides of the container. So the pressure of the gas will increase. And then if you lower that temperature, okay, basically you're giving the gas a sedative. So it's calming down. So it's not bouncing around as much, so it's not creating that pressure inside the container. So this formula is written as P1 over T1 equals P2 over T2. Okay, where P again is pressure and T is temperature in Celsius. Okay, so here's another example here. Okay, so we have our volume is constant and the amount of gas is also constant. So if we have a low temperature, okay, this is in Kelvin, which is actually the same type of scale as Celsius. So this is 200 Kelvin, okay? So it's not a lot of heat. This is actually relatively cool, okay? It's actually below freezing, okay? So you've got 1 atmosphere of pressure, which means that these gas particles are still moving around. They're still kind of pushing up against the sides of the container, but they're not going crazy. So you don't have a lot of pressure. But then if you double the temperature, okay, so now we're up to 400 Kelvin, you're also going to double the pressure because it's increasing that movement inside the container. Okay. All right, so the third law is Charles' law. So this relates temperature and volume. So in this case, again, we're going to hold the amount of gas constant, and now the pressure is also going to be constant. Okay, so this requires kind of a moving piston to keep that the same. All right, so the volume of a gas increases as the temperature increases. So this is the same kind of thought process on the last that there was on the last law, the Gay-Lussac's law. So in this case, you're increasing the temperature, so your volume or your gas starts moving around more. But in order to keep the pressure constant, it means that it has to be able to spread out more. Okay? And then if the volume of the gas decreases, okay, the temperature is going to decrease. So they'll decrease together. Now, because they're both moving in the same direction, as one decreases, the other decreases, it's another one where you have V1 over T1 equals V2 over T2, where V again is volume, T is temperature. So here we've got our moving piston that will keep our pressure constant. So when the temperature is decreased, the gas particles move more slowly. They don't hit the sides of the piston as much. They don't hit with as much force. So as a result, the volume will decrease in order to keep that pressure constant. Now when the temperature is increased, those gas particles start moving around faster. They're hitting the sides of the piston with more force and just going kind of crazier. So the volume will have to increase in order to keep that pressure constant. Okay? Now, when you combine all of these gas laws, you get one law that relates the temperature, pressure, amount of gas, and the volume. So it's called PIVNERT, actually, it's how we shorten it. It's pressure times volume equals N, which is the moles of gas, which we'll get into later what that all means, times R, which is a constant, times temperature. So P is in pressure, V is volume, N is the moles or the amount of gas present. R is a constant, so it has a value based on the other units that you're using in the problem. So it's either 8.314 joules per mole Kelvin, or this is the one that we're going to use more often, R equals 0.0821 liters times atmospheres over moles times Kelvin. Okay. Now the thing to note about this constant here, okay, it means that your volume has to be in liters, your pressure has to be in atmospheres, moles are always going to be moles, but your temperature has to be in Kelvin. Okay, and then of course T is your temperature, right? So if you forget what units you need your pressure, volume, temperature, anything in, all you have to do is look at this constant, which will be given on your test, so don't worry about that, and then look at the units that the constant has. Okay, that will tell you immediately, all right, I need my volume in liters, I need my temperature in Kelvin, and my pressure better be in atmospheres. Otherwise, this constant will not work. Okay? All right, So you've got your combined gas law is P1 V1 equals N1 R T1. Okay, so now in this case, we can use the combined gas law to really calculate the changes in any and all of these conditions. So if we're changing the pressure from one reading to the next, if we're changing the volume, the amount of gas, or the temperature, okay, you can do that. Now, what's really nice about doing the combined gas law this way, okay, is anytime you hold one of these constant, you can just cross it off. Okay, so R, for an example, is always constant. So R is a constant, it will cancel on both sides. Okay, so you can just go ahead and get rid of it right now. And then you get P1 V1 over N1 T1 equals P2 V2 over N2 T2. All right. Now, if say you were going to hold the volume constant but change the other three variables, okay, you just go ahead and knock the volume out. And then it would be P1 over N1 T1 equals P2 over N2 T2. All right. So I really love using this formula when I'm talking about the gas laws, because then it's only one formula that I have to use. I don't have to take 3 different formulas and keep looking at, okay, do I need to use this one or this one or this one? I just have one that combines all of them. Now, if you're more comfortable with only dealing with 2 different types of variables at once, you can definitely use that until we start working with 3 or 4 variables at once. Okay, so either way you want to do it, it's perfectly fine. All right, so that is the end of this chapter, and we'll be working on some more of these gas law problems in class, okay, for one of your homework assignments. So we'll be working on this together.